Hi, I am François Nerido, and welcome to the Boston List meeting of 2012, June 28th at MIT. I'd like to thank Professor Sussman for having us here at the MIT. And today, our speaker is Kalman Reti, who will demonstrate for us Symbolics list machines. So, Kalman, thanks a lot for coming, and the floor is yours.
Oh, thank you. I have a bunch of slides, which are probably way too long, and I'm going to skip some and go through them quickly. I'm also going to demo some stuff, which is also probably way too long, and which I'll probably go through quickly. But if anybody has any questions or wants to know more, you can contact me at my Gmail address. So what's a list machine? Well, it's a single-user workstation, an old single-user workstation that's basic goal in life was to optimize the development of software in Lisp. And it, for its day, was a very forward-looking thing. It sounds prosaic these days, but it had a high-resolution black and white bitmap display and a keyboard with lots and lots of extra keys, a mouse, three-button mouse. All of that stuff was new. But the most important stuff about the Symbolics Lisp machine, and which wasn't shared by the other variants of Lisp machines, was that there was an incredible amount of software and developed at Symbolics. And there were several hardware innovations in the architectures of the Symbolics versions of the Lisp machines that were also pretty unusual and interesting. So that's what I'm going to concentrate on in this talk. So at Symbolics, we had essentially four models of Lisp machine. The first was called the LM2. It was a repackaging of MIT's Catter, which I'll talk about in a little bit. The second one was called the 3600 because it was a 36-bit machine, and the 00s were for the fact that we had planned to have multiple models that have different digits down there. The next one was called the G machine internally. It was the same architecture as the 3600, but it mostly was intended to make use of gate arrays and commodity parts for serial and Ethernet and stuff like that. All of that logic had been done in discrete logic in the 3600. And so now there were chips available, and we could therefore build it smaller and cheaper and hopefully a little faster. But at the same time, we started work on a single chip Lisp machine, which was the Ivory, which was yet another architecture. And then the very last thing of the original Symbolics company was the emulator for the Alpha, for the Ivory that ran on the Alpha. And then Brad Parker, who's sitting back there, wrote this absolutely marvelous hack that allowed that Alpha emulator to run on any 64-bit machine. And so that's what I'm going to show on my laptop. So how did how did Lisp machines come about at all? Well, in the 70s, and people like Jerry can tell more detail about that, research was running into a problem, AI research, because the Lisp resources were limited. PDP-10 didn't have a lot of address space. The instructions necessary for doing runtime type checking often dwarfed the actual cost of doing the operation, so it wasn't very efficient. And a researcher could easily use up a whole PDP-10 for hundreds of thousands of dollars, and that was a little too expensive. So the first attempt was a machine called Cons, which wasn't ever built. Some of the ideas from it were put into a machine called the Catter, which got built. Notice the name. It was built in '79, and I don't know exactly how many were built at MIT. I've heard numbers anywhere from 8 to 12 or so. Right. And they cost between 50 and 60K per researcher, and they were much better at doing Lisp software development than the PDP-10s, so they were a big win. But visiting researchers saw them and said, hey, we'd like some of these, and MIT didn't want to be in the business of manufacturing computers, so they licensed the Catter design to two startup companies, Lisp Machines Inc. and Symbolics. Russell Nofsker, Tom Knight, Dave Moon, Dan Weinreb, Mike McMahon, and Bernie Greenberg were all at Symbolics, and Richard Greenblatt and some other people, but I'm hazy on the names because I only worked at Symbolics, were at LMI. And each company started out selling essentially the Catter. And each company also immediately started on a successor Lisp machine. The Catter that Symbolics did was repackaged we laid it out on PC boards and put it into an industrial box, but it was essentially the same design. The Catter was more or less a vanilla 32-bit word machine, which wasn't the most usual thing at the time. But it had two great features. One was a very large microcode store, and that meant you could make a microcoded instruction set that was essentially a Lisp interpreter. So car was an instruction, as were lots of Lisp primitives. And it had large scratchpad memories so that this microcode could look up lots of stuff, and that was used for the type checking parts. And the other interesting feature was that you could microcompile a Lisp function into microcode. And the reason that worked was that there was a hardware stack, function call stack in the microcode. So I think it was only 4 deep. And so you could call the exact same micro instructions that implemented the car instructions after you had fetched it, decoded it, and then dispatched off to those things as a subroutine called by your microcompiled larger function. So you could take your inner loop of some computation and compile it directly into the microcode. The other really cool thing about the Catter was that when it was halted, that is not fetching macro instructions and interpreting them, but still powered on, you could actually access its memory through these parallel cables from another machine. So you had a debugger on another Catter that could look at the stack and poke around in memory and figure out why you crashed. But it could also find your ZMAX modified buffers and write them out, which was pretty amazing. So both companies, as I said, started successor machines, and LMI's successor machine was more or less the same architecture with faster technology, so they got a performance boost. Anyway, Symbolics' successor machine was an attempt to do an improvement on the architecture. And the main improvement, there were many little ones, and I'll talk about some more of them, but the main improvement was to take the tags and put them in every word in memory. Some of the Catter floating point manipulations use 32-bit floating points with no tags, and the trouble is keeping track of those in registers and in the garbage collector was a pain, and it sometimes got it wrong. But by having the tags in every single word in memory, and by carrying the tags through the data path, and having special logic in the data path that could look up these tags. So what you had is, let's say you were doing an add instruction. You took the two operands and presented it to the integer adder logic, and you presented the operands to the single float, adder logic, and the tag checking hardware basically looked it up and gave you an answer saying either use the integer result, use the floating point result, or take a trap so you could coerce one to the other and then restart the instruction correctly. The important feature of that was that even by having elided out the instruction fetch overhead for instructions to do tag manipulation in the Catter, it didn't have to do it as macro instructions, but it did it as micro instructions. So in terms of microcycles, you did some tag checking and then you did some operating, tag checking, then operating. Whereas the 3600 was tag check and operate every cycle. So you basically moved the overhead for the runtime type checking from the time domain into the hardware domain. You had to spend 10% more gates. So the upshot was that the 3600 was almost exactly the same technology and number of gates as the LM2, but was 4 times faster. So one of the other things about so we had 36-bit words. That was what allowed us to put tags on every word. But we wanted to have 32-bit fixed nums and single floats. So that meant something had to give. And what gave is that there were two 16 tag ranges set aside for fixed nums and for single floats, so that the low order 4 bits of the tag value were actually the higher order 4 bits of the data value. That still left a goodly number of tag bits around. And as I said before, every word in memory had tags, which made the garbage collection a lot simpler. There was hardware support for hashing that was used in method dispatch. That turned out to be not all that useful and was dropped. But there was also hardware support for ephemeral GC, and that took the nature of, if you stored an ephemeral pointer in a page that was not ephemeral, you remembered in a page table bit that you had done that. And so instead of having to chase roots and find all of these things, you had this oracle that said, this is the set of pages you have to scan for such things. And that was a very big win. There was also support for what was called an address space number register, which was basically another 8 bits tacked on to the virtual address. All of the software in the Lisp machine was in one address space, including all of the operating system routines, all of your device drivers, your compiler, your own code, all of the what are would be considered utility processes. Everything was in one address space, which made it very easy to share data among processes and things, but it made it hard to separate data. And one of our customers wanted to be able to do that, and encouraged us, and in fact, so almost demanded that we add this address space register, and they were going to write the software to support it. They never did. We never did. It got dropped from later architectures. So the 36 hardware itself was 5 large boards like this, just to implement the processor. And then in addition to those 5 boards, there were another set of large boards for the memory. And at the beginning, the memory was like 16K words, 36-bit words. And by the end, we had boards that were as high as 512K words. And depending on the size cabinet, you could put anywhere from 3 or 4 to 6 or 8 memory boards in your machine. So at the end, you could get a decent amount of memory. But at the beginning, the machines were really, really tiny. There were color boards. The IFU, one of those 5 boards that implemented the processor itself was intended to be the IFU from the very beginning. This is an instruction fetch unit that prefetched instructions, pre-decoded them, and prefetched some operands and put them in sort of scratchpad memory so you could access them. But it was late, and it was very, very, very complicated and very, very tricky to debug. So it actually didn't ship with the first 3600 model. So in the later models, there was 36XX, 36X0, and then there was a 36X5, and the 5 meant that you had an IFU, and it was quite a bit faster. We also made color boards. Color at the time was a separate monitor. We made 8-bit color boards for CAD, drawing type applications, and 24 or 32-bit color for animation and rendering, paint. One of the things about the color system, which was developed by the color division out in Westwood, California, was that they had ties to the movie industry, and so we had the ability to genlock to a house sync, which was unusual at the time for computer graphics systems. And moreover, we could basically diddle our microcode easily. So some of the displays that you saw in some of the early Star Trek movies were done by Lisp machines because we could genlock to a 24 frames per second house sync, so they would be in sync with the cameras. We made an array processor board for doing high-speed floating point calculations. We did a 386 daughter board that you could basically use to load and test 386 programs. We did various interface boards to different Unibus, GPIB, SCSI for controlling various instruments. The 3600s came in really tall cabinets, like this tall, and then slightly smaller cabinets, and then half-size cabinets. And more or less, the only difference was the amount of expansion you had. So, as I said before, all the peripherals were discrete logic. So the Ethernet was done out of logic gates, and the serial controller was done out of logic gates. But after a while, it became clear that you could get a much smaller product by using commodity chips. So while the biggest 3600s were this size, the biggest of the G machines were this size, and there were smaller ones than any possible 3600. But it was exactly the same architecture. So, by putting the logic for the processor on gate arrays, and by using commodity chips, or rearranging things a little bit, we got it down to 2 boards for a processor. And then at the same time that the G machine was being designed, we made the Ivory chip, which was a single chipless machine. It had several absolutely amazing innovations for the time. It had 40-bit words, which meant that now you could have not only 32 bits of data for fixed nums and floats, but you could have 32 bits of address space. And this was 32 bits of words, which was significantly large for 1986, 87, whatever. But because it was a single chip, there were 2 features of the previous machines that we had to lose. One was we couldn't have a loadable microcode. It had to be basically ROM burned onto the chip. So it had to be right the first time. And secondly, it couldn't be very big. It couldn't have all of the stuff that the large microcode stores of the predecessor machines had in it. So things like bitblit and big number arithmetic, which had been in the microcode on the 3600s, had to be moved out of microcode on the Ivory chip. And the problem with that was that they really wanted a very high-speed access to moving lots of data around. So Dave Moon came up with this idea called bus address registers, which were sort of like a single word fetch ahead or right behind channel. You loaded it with an address, and in idle cycles on the bus, it would either fetch that and store it in a local register or write it out. And there were idle cycles on the bus because the instruction set consisted of half-word instructions. So when you fetched a word of instruction data from memory, you got two instructions. So that was at minimum 2 cycles. And so you had some idle cycles there, hopefully, that you could send the data through. Another innovation in the Ivory was that we didn't have any constant tables. In all the previous architectures, for every function, if you wanted to push a constant to either pass to a function call or to use some operation on it, you had an index in the instruction, which was some number of bits wide, that was an index into a table of constants that was attached to the function. The trouble is that wasn't very many bits, and it was very easy to write a function that overflowed it. The compiler tried to break up such functions into subfunctions that had non-overlapping subsets of the constants in their tables, but it's pretty easy to defeat that, and it got it wrong a lot. So for the Ivory, instead of having a constant table, we said, okay, instructions have a tag that says I'm an instruction word. Anything else that's in the instruction stream means push me onto the stack. So if you wanted a constant on the stack, you just included it in the instruction stream. But that caused a slight problem because the constants were all full words and the instructions were all half words. So now you had to have this cute, again, this was invented by David Moon, cute trick to, for example, do the first half of an instruction, skip down to the next word, push that whole word, go back to do the second half of the previous word, and then skip over the full word to do the first instruction of the next word. And the encoding of those, how to advance the PC was done by the coder code bits. The original use of the coder code bits was to allow you to store n words of a list in n words. And not only that, you could store n words of a list in n words and have an array that pointed to the same storage so that you could index it as an array or operate on it as a list as you saw fit. I was mostly involved in designing the VLSI tools that led to the Ivory chip, so that in most of this time that I worked for Symbolics. So I know a lot about the whole design process. And it was sort of an example of what was great about the Lisp machine. Each designer had a Lisp machine with the entire design of the chip loaded up, and he was working on pieces of it using tools that we had built. None of the tools on Unix at that time were up to it. And moreover, we used a methodology that was different. Instead of doing layout that was specific to a particular process, we did what we called sort of generic layout. And then it knew there was a 2-level metal CMOS process, but it didn't know anything about the constraints. And we had a compactor tool that you fed it the exact dimensions that you needed for spacings and surrounds and all of that, and it would take your design and squeeze in all the space and get it to the smallest layout given those constraints. And because of this methodology, we were able to do 5 different revs of the chip on 4 different technologies, which was pretty amazing. We also had all sorts of simulators. So we had an instruction level simulator where somebody said this is how the instruction should work. We had a gate level simulator, logic simulator, and we had a transistor level simulator that simulated the transistors as resistors and figured out what the thing was. And we even had SPICE, which is a Fortran program that actually figures out the waveforms for the analog parts. And in fact, one of the cute things about SPICE was that we had a Fortran compiler on the Lisp machine, but because the Lisp machine has tags for everything, if you don't initialize a variable, you get a trap. And we found that there were whole bunches of bugs in SPICE because there were whole bunches of uninitialized variables that got used. Anyway, the designers would come in every day, load patches, and work on their designs. But many times, when they loaded patches, that would change radically. Thousands of objects that they had. They grew new slots. They changed, types. We loaded whole new tools. We replaced whole new old tools. And the designers just didn't care. They would come in, load patches, and continue working. And that was a pretty amazing. The other strength of the Lisp machine was that we had super. In addition to control, we had meta, super, and hyper Bucky keys on both sides of the keyboard, and we had a 3-button mouse. And the design system allowed you to draw, and you could click on any mouse button with any combination of these things, and they would do different stuff. So once the designers had actually learned how to use this, they could go really fast and just do amazing stuff in a very short amount of time. Not the modern interface style at all. Anyway, so as a validation of this design process, the very, very first prototype rev of the chip, which was on a really huge die and would have been ruinously expensive to actually make, almost completely worked. The only real bug was that one of the transistors driving the virtual memory control signal that had to cross the entire chip was sized too small, so that basically out in the boonies it got noise, and so we couldn't turn on virtual memory. But everything else worked. And so for the trade shows that we went to with this, the first few prototypes of this machine, we just packed it full of memory and didn't turn on virtual memory. So the only other thing I want to say about this is that we took about 10 to 12 man-years to do the Ivory chip. And the only comparable chip contemporaneous to that was the Microvax at DEC, and I knew some people who worked on that, and their estimates were that it was 70 to 80 man-years to do the Microvax. That, in a nutshell, is the reason that the Lisp machine was great, the Symbolics Lisp machine. So another point is that if you were using Unix tools, the standard thing is you take some internal structure that you've created in your tool, you thread it through the needle of piping it out to a single 8-bit stream, to pass to another tool, which is going to take these 8-bit bytes and create some data structure, and then operate on that. Whereas in the Lisp machine, we just handed a pointer to the data structure, and each tool just traversed it the way it wanted to, and made annotations wherever it wanted to, and that was it. So Symbolics added a lot of software. When we got the original system from MIT, it had command Lisp listeners, and it had Zemax, which is an Emacs-like editor written in Lisp, and lots of individual tools like an inspector and band transfer and various things. And I'm going to demonstrate some of these things. Symbolics added a command processor, and it has a fairly powerful model of how to do input-output, which was invented by Mike McMahon for dynamic Windows, but which is also used in CLIM, which was intended to be a portable equivalent. And it has a robust local file system. Bernie Greenberg wrote that, and it had the interesting feature that every block written to disk had a couple of words at the beginning and end that were called check words. They weren't like a checksum. But the point was they gave the unique ID of the file and the word displacement into the file. So if you read the wrong block off disk, you knew it. And in fact, I was once working in Chatsworth, where the manufacturing facility was, when one of their main file servers had a disk that would give you block M when you asked for block N with about a 10% probability. And all it took was 2 lines of code while the machine was running to have it retry a few times till it got the right thing. And then all it took was another 6 or so lines of code to basically, every time it touched something on the bad disk, write the same contents to a new disk that we hooked up. And so just by reading all the files in the file system, everything got migrated to the new disk, and then you just changed the configuration that pointed to the new disk, and everything was fine. There's not many file systems that you can say something like that about. More software. I'm not going to say anything in detail about them, but suffice it to say, there was lots. There was a compiler framework that was used to do C, Fortran, and Pascal. There was a whole separate compiler that did Ada. I believe that the first three shared a lot, and the Ada compiler was a totally separate entity. And of course, there was a prologue as well. Some of the debugger stuff I'll show you. There was a whole thing for the documentation. When you got a Symbolics list machine, there was about 4 feet of manuals. Those manuals came from the documentation system that was written on the list machine, and more was available on the list machine. Now again, these days, online documentation isn't much of a big deal, but back then, in the 80s, it was a big deal. Yes, and not only that, you could click on examples and they would run. And of course, we had other outside programs. Symbolics acquired Maxima and converted it to Common Lisp and added lots more features. It was then spun off to another company. We wrote a rule-based system called Joshua that its main claim to fame was it was totally object-oriented, and you could plug in pieces for the database and for the truth maintenance system. Basically, you could hook it up any way you wanted, and it was a very powerful system. There was a def system facility in the original MIT list machine, but it was totally rewritten and intensified the system construction tool. And the basic idea is that you could define systems that were collections of systems and load patches and distribute them and distribute patches over email. Just whole lots of hair. I'm not going to say anything about that. So the last thing that the original Symbolics wrote. So there were 3 Symbolicses. The first Symbolics was a public company, and in about 92, it filed for Chapter 11 bankruptcy, and then it sputtered on for a while, and then finally filed for Chapter 7. Its assets were bought from the bankruptcy court by a Princeton firm called Princeton Capital, and they started a company called Symbolics Technology Inc. And I was hired as the developer for that company. And our main job was to bring out the next version of the alpha emulator. The old Symbolics had gotten 1.0 out the door, but it had many rough edges and didn't support things like status, which is the relational database, and didn't support a whole bunch of stuff. And so the emulator, though, had a couple of cute features. One cute feature was that it pretended it was a newer rev of the alpha chip. So that meant the Ivory chip, so that it could pretend to have these coprocessor registers, which really represented stuff that was done on the C side in the life support code rather than done in fetched and emulated Lisp instructions. And the most important part of that was the scanning pages and transporting old pointers to new space. And the other cute trick was that instead of mapping the 40-bit words directly as 40-bit words into the virtual memory address of the alpha, it mapped the 32-bit parts contiguously and the 8-bit parts, all the tags, contiguously. So when you needed to, in C code, access a range of integers, for example, like in the communications buffers that allowed life support and the list machine to exchange data, it was in the natural format that C expected it. So that was a cute idea. So the VLM stands for Virtual List Machine. The life support was written in C, and the emulator was written in what I call parenthesized alpha assembler. The idea there was this fairly large Lisp system that had lots of macros for little sub-pieces of what had to be implemented to do the instructions. And those macros expanded into basically parenthesized alpha instructions. And then there was a mechanical translation into the format that the alpha assembler wanted, and then you assembled them and you included that as an object in the actual executable. The intention was that if you wanted to port it to another architecture, you would change those macro expansions to expand into parenthesized something else instructions. And in fact, there was an attempt at MIT to do that, exactly that, for the PowerPC 64-bit chip. And it got far enough, it got mostly done. It got far enough that you could actually run some things in the cold load stream, but it never quite worked. But Brad back here had the brilliant idea to, instead of expanding into instructions for the native thing, he just expanded into subroutine calls to a little C backend that pretended it was an alpha. And so that's the emulator that we're going to see running on this laptop. And it's faster than any Lisp machine that ever existed on the planet, any real Lisp machine. Not on this laptop, but believe me, it's pretty impressive. So now we're going to go to the demo. And the first thing I want to do is start up another Xterm and boot the Lisp machine. So I'm booting a particular world of mine that I have to type the right things. That has a whole bunch of my own hacks in it, but that's because I know how to do things in that world. That's the one I typically use all the time. Notice in the bottom left appeared a minimized little window. That's the cold load stream window. On a real life Lisp machine, it used the same bits as the bitmap display in a mode that's very much like the consoles on Linux. That is, you could switch to this area of the bitmap or switch to this other one. And the cold load stream was a character only interface. And if the Windows system wasn't working, you could get into the debugger there, figure things out, do a lot of commands. Let me scroll back before you take pictures so you can see the Symbolics Open Generator 2.0. Notice that as I move my mouse around here, different things highlight. And underneath, so at the very bottom, you'll see there's a date and time clock, and where it says CL user, that's the package that the current process is in. And where you see user in backput, that's the state that the current process is in. But above that, you'll see this two black lines that show what mouse clicking certain clicks will do. So it says right now, mouse left would show a list of programs, but if I move it up to here, mouse left will select the document examiner activity, which is the activity that lets you view the documentation. And one of the main points I want to make in the demo is how that works. But even so, as I move over here, you see lots of different things going. Plus, underneath it says, to see other commands, press Shift, Control, Meta. So here I'm over this select D to select the document examiner. By the way, the lozenge select that's right under the cursor, that represents a key. On the Symbolics keyboard, there was whole bunches of keys. So there was a select key, a function key, and there were bunches of modifiers. I already mentioned super, meta, and hyper. But there was also symbol, and that allowed you to type like Greek letters or less than or equal as one character. And all of those keys did things that it's very hard to map those to modern systems because there's just not enough keys. And moreover, most GUIs usurp enough of them that you don't have enough left over to do it. So one of the things I first have to do is log in as me. And that will set up the keyboard the way I want. And so again, I'm going to go up here and notice I'm highlighted here. I'm going to push down the control key and notice two things happened. One, the text at the bottom in the black changed. It now says control mouse left will mark a region starting with this position. But the highlighting also changed because now it's only highlighting the letter P. And the reason for that is that on the Lisp machine, the connection between the characters that appear on the output display and the objects that engender them are not broken. That connection is remembered. And so, for example, if I make a list, if I can type, this keyboard is being a little balky. It's also not the angle I'm used to typing at it. List, the symbol A, the string B, and the number 1, 2, 3. Well, it would have been 1, 2, 3. So I have this nice little object. If I present that object as an expression, which is a very general purpose type, notice one thing, as soon as I type the closed parenthesis, it finished the form, because we're sitting at a command prompt which is waiting for either a command or a Lisp form to evaluate. This is a read eval print loop. And so because I typed open parentheses and some stuff, it knew I was typing a form, and as soon as I typed the closed parentheses, it knew the form was finished, so it evaluated it. So the presentation started exactly to the right of that parentheses. If I try to accept now something of type string, notice when I move over here, the string is highlighted by the mouse, and I can click on it to accept that string, but the A and the 1, 2, 23 aren't. Let's click on the string and get it. If I instead say I want to accept an expression, I can type it again. Now, not only is the B highlighted, but the 1, 2, and 3, and the A, and indeed the whole thing. And the reason when I did the present, I got back this displayed presentation object. And so I'm going to describe that by clicking middle. And you'll see that it has a recursive structure, and each little text displayed presentation object represents a little piece of that presentation that was displayed on the string, and keeps the mapping between what's on the screen and the data. And that allows me to do cute tricks like if I go up here and do Control Meta Right click, I can type 42. And now if I type foo, it's been changed. If I type accept expression and click on the whole object up here where I presented it, it is indeed foo. So what the command prompt is doing is it's trying to see, are there objects that are visible on the screen which can be translated into reasonable commands or reasonable arguments to commands? So I can type the beginning of a command, so I'm going to type st space, and it completed for me because it knows that all of the things that start with st space have an A following them, but it didn't complete very far because there's multiple possibilities. But if I type G space, it now knows that it's the start GC command that I was trying to do, because that's the only command that fits all those criteria. And then it prompts me for some keywords. Now, this paren keywords is what's called a noise word. It's a prompt, but it's not really part of the output, because if I hit rub out, it goes away. If I type it again, it comes back. So it's there to help you, guide you along the path of getting the command arguments, but it doesn't get in your way. If you don't know what keywords it's wanting, you can type Control/ and it lists them all. And in fact, I can click on one to supply it, because remember, now I'm in a context where I want a keyword, and so it knows that those things are mouse sensitive and can be used. And so I'll say yes, I want to turn on the ephemeral GC. Now if I type Control/ to see what keywords are available, notice the ephemeral one isn't there anymore, because it knows I've actually supplied it to this command. So this type of intelligent command completion, it's very hard to explain, but it quickly gets very automatic to use. And so I'm going to say dynamic yes. So yes, it is. There's nothing, I don't know of any other system that has anything like this. Klim does too, but Klim got its ideas from this. So now I turned on the garbage collector, but nothing happened. Well, that's because usually we don't garbage collect until we need to. So I'm going to actually cause it to garbage collect. And I want to show you another feature. Except I can spell and talk. GC flip now. So as soon as I type the closing paren, it's going to happen. So I want you to look where it says user input. And notice it changes to run because now we're in the run state, but we got these little bars underneath. There's a bar underneath the run that's called the run bar, coincidentally enough. There's a bar between the run bar and the one that's under Common Lisp SI, which is the package that we're currently running in. That's the disk bar, which we don't see. And the bar that we're seeing right now is the transport bar. And there's a scavenging bar that comes to the left that should appear momentarily as we start garbage collecting. So the idea of the garbage collector on the Lisp machine is that it's written in Lisp. it has to run while you're running. So it can't stop the world. So it's a copying garbage collector. And what you do is you take all of the memory that you've got objects in that you want to garbage collect, and you create another space that's the same size in case all of them happen to be non-garbage. And you call the old one old space, and you call the new one new space. And then you arrange for the hardware to make a trap so that every time you touch a pointer in the old space, it gets copied to new space by the trap handler. So anything that touches any object in old space will copy it to new space. Now, the list machine has a fairly large array of primitives, including locatives into the middle of objects and arrays. So you can have a pointer that points into the middle of something. So that has to keep working because, remember, you have lots of programs running. So what the garbage collector does is it leaves behind what are called GC forwarding pointers. So when the locative pointing to the address that was the address of the object in old space hits one of those, it says, don't look here, look over there. And so then the data gets actually fetched from the new space location. And so in the background, all you have to do is have something that wanders through all of the possible paths to known objects. And once it's gotten all the way to the end of that process, you know that everything's been copied from old space to new space that's accessible. And you just declare, oops, the old space is done, it's free. And the new space now is and while you're doing this, new programs, new consing happens in new space, of course. So programs can continue to run while the garbage collecting is happening. So notice while I was talking, it finished. It gave us these little things in square brackets. These are called notifications. They're asynchronous, and for a Lisp listener, it doesn't hurt to have them pop up because if you were sitting just at a command prompt, it'll repaint the command prompt and you haven't lost anything. If you were in the middle of typing a command and one of these happens, it blasts the notification and then retypes what you typed because it knows how much you typed, so that doesn't hurt anything. But for other programs, you might not want those to happen, so they can be turned off. And there's a separate notification window, if I could type, that they're all collected in. So you can go back and find out about these later. Or if you're in a context where they can't be blasted to the screen that you're looking at, you can get a pop-up notification window that's created on the fly with the notification. One of the other things about the list machine that I wanted to demonstrate is that, so when I said present before, I could have typed Control-Shift-A, and that gives me the list of all the arguments. All of the names of local variables and arguments are always saved. There is no such thing as a difference between a debug build and an optim build on the list machine. You always have symbols for everything. So when you're describing an object, you get the names of the slots. You can click middle on any slot, and you'll get the description of that thing. And so you can go click, 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 chasing a chain of pointers faster than I can describe it. But in addition to this, which is, there are other systems that can do that, you can do Meta Shift A, which instead of just giving you the short description, gives you the actual documentation from the manual. So I'm going to actually go to the document examiner, which, because this is a smaller screen than usual, so anyway, so these things down here are the document sections, and we can search for them. So show candidates for present, let's say, and it lists all of the things that match present. And so there's a lot of choices here, many of which you probably have no idea what they mean. Certainly, I don't know what all of them mean. So what you can do is you can go click middle on them, and you get a little graphic that says where these guys are. So you can find the location in the documentation that actually matches what you're interested in. Now, this is better with a bigger screen. So I apologize. And notice when you do this, it remembers the level that you came from, and it shows you the detail of the next higher level, but it elides some. So if I click middle here, I won't be seeing all of the stuff. So it doesn't get infinitely complicated, because the whole point of this graphical display is to make it easy for you to select locally in the context of the documentation to get to the right place for. And then, of course, when you get there, you just click on it and you you read the documentation. Now, as I said before, this documentation has graphics, drawings in it. It has links to other, so each section is basically a link to the other one, just like, so using data arguments, present, it highlights, and I click on there, I go to the documentation of present. But it also can have examples that it can run. So, and the program that allows you to create those is called Concordia, and it again was written at Symbolics, and it allows you to have markup. So if I say medx add section, oops, if I could spell section, it would help. This keyboard is being balky. Well, okay. Maybe it's create section. One of the other problems is that because this is a laptop, many of the keyboard layout keys are intended to be used on the keypad. And of course, now I have to type functions something to get those. Anyway, I can create a record. Record title foo for demo. And it's to say, oops, well, that's not good. Well, at least we get to see the debugger. So I was going to show the debugger in a different way, but why not? So once we get an error, we go into the debugger. And the debugger is really one of the more powerful aspects. Again, it uses the same presentation type thing. So if I type Control B, I show the backtrace. And so this is the this guy down here at the bottom called this guy, who called this guy, who called this guy. And they're all mouse sensitive because I can go to any particular one. So this is not actually a particularly interesting one. So let me go to the one that I was going to demonstrate the debugger on, because I have some. So the way I was going to demonstrate going to the debugger is that there's actually a bug in this. Remember when I was mousing over these things? Oops. Somehow I'm not in the right context. When I was one of the other things I wanted to show is, notice as I move over the scroll bar, there's this horizontal line of short dots. This allows me to say, I want this line up at the top of the screen, or I want that line at the bottom of the screen, and it does it directly. Modern user interfaces, you have to scroll, and of course there's this feedback loop, and if you're doing it over X or a slow network connection, or the CPU got way faster, it's sometimes hard to get it to go exactly right. And but here you say directly, move this to here, and move that to there. I really like that. It's not very common, and of course it works in the horizontal scroll bar as well. So it's less useful for text than it is for graphics. But anyway, that was just an aside, because what I was trying to do is get back to the beginning. So when I was mousing over these things, I was carefully avoiding mousing over this. See where it says loaded from, and it gives me a path from the world name. If I mouse over that, I go into the debugger too. And this is a slightly more interesting thing to look at. So the error we got was we got an unclaimed message. That is, we sent a message to an object that didn't handle it. So these first three are all for handling that. So this is the guy who did it. So Control E will take us to the editor with the function there. And we can look at it, and we'll see that this is a function called fep pathname realhost, and it's given a path name. And we send that path name a host message, which gives us back something that we also send a host message to. And on the original Lisp machines, the FEP, the front-end processor, was a 68000 that loaded the microcode. And all the world files were on the file system that was a very simple file system that little brain 68000 could understand, which was called the FEP file system. And so there was one FEP file system per disk. So you had FEP0 for the first disk, FEP1 for the second disk, FEP2 for, and all of them, of course, resided on one machine. So when you have a FEP path name and you send it a host, you get one of these FEP0, FEP1 things that indeed can support having a host message sent to them to tell them the real Lisp machine host, right? But what we were given, if we look at the frame, is we were given this path name, which is a Unix path name, because this is a Unix emulator, a Linux emulator. So, and the world is on Linux, and so one of those doesn't know how to do this double indirection. So we can fix it. But it's probably not the fault of this guy, because this guy is clearly expecting only a fep path name. So whoever's calling him is the one in error. So I just said go down to the next stack frame. Notice we have all the local variables with values. We could click middle on them to describe them, to look at the data structures. And I can type Control E to go to its source, which is in a different file. And notice this is actually only a piece. This is a macro. Control Shift M shows us the macro expansion. And this is the tester method. That's the middle part here that we're looking at. And it comes from this tester clause here. And what it's doing is it's saying, if you take the path name, get its real host, and see if that's not the local host. And if so, make the tester method return true. What the tester is doing is, as you're moving the mouse around over these objects, there's all these possible translators that are live that could translate into a command. And the tester's job is to see if this particular object is applicable to this translator. And so if the world was on your own machine, the command that it's trying to do, which is copy world to this machine, wouldn't make any sense. So the tester should return nil. But if the world is a path name on some other machine, you might want to copy it here, right? So it makes sense to make that a possible command. So the issue here is, of course, that this assumes that all world path names are fep path names. So we can fix it. Type P path name. And let's say I don't remember exactly what the type of a fep path name is. One of the nice things about the editor is that you can always go into a command loop. So we can just perform an experiment. Parse path name fep0 foo dot bar, and then do type of that. And there we have it. Now, I'm going to use that control mouse click that we saw before, because that allows me to actually mark the characters that are that presentation. Notice before I did control, the whole thing was highlighted because I had a connection to the object. But by pressing down control, I'm now talking about the individual characters. So I can slice and dice whatever way I want. The individual characters is the only thing you'd get on a traditional output. And then I just put it on the kill ring. I can hit resume, which is a hard one to type on this keyboard. I think it's this one, yeah. And yank that back in and add a closing parentheses. Now, Control-Shift-C will recompile it. And so it compiled it, a new version of this whole macro expansion, which included several functions. And going back to the debugger, sorry, what? Oh, you're right. It should be if or when, right? Yes, you're right. It would have made a problem, which we would have found in the debugger, and yeah, we would have fixed it. But okay, yes, you're right. It's hard doing this and talking at the same time. Anyway, so now we're back here. I can just re-invoke this function, and it's going to invoke the newly created one. So I do that, and it didn't work. Sorry, what? Ah, you're right. So when I think is correct, because I want to say nil in all cases except if it's a fep. Oh, no, yeah. When it's a fep path name, then this test is the answer. Otherwise, it's always nil. And I did leave out a paren. What? I don't know what I just did. Oh, it does. It's blinking the matching one. And if I were to save it out, it would have told me I didn't have balanced parentheses. And I'm not going to save it out. But the next step that I'm going to demonstrate would have also told me. So anyway, we can go down to the presentation handler and run it again. What did do? Yeah. Anyway, yes. Sorry about that. But the next thing I wanted to show also sort of depends on getting it right. If this were Symbolics and I was actually in charge of fixing this bug, I would just say start patch, MEDX start patch in the editor, and I would create a new patch version for this particular system. It knows which system. It remembers which files each function comes from, and it remembers which systems loaded those files. And so when I say MEDX start patch, it would tell me that this needs to be patch 1, 2, 3 to some particular system. But each system had a notion of who owned it. And since I'm not at the Symbolics site, I can't do that. But I can do start private patch, which means my own local patches, which I can load from my list init. I can say local demo patch, which is a Lymphus running on this list machine. And then I give it a comment, fix world mouse over blowout. And so now it's opened up a file for me, and then I add patch, this function, and I can say what this function is. There's only call FEP specific function on FEP path names. And then when I say finish patch, it will write out that file for me. This is another example of the object-oriented except present thing. This is a set of values. I can click on any of them. It's already got me as the patch author, but a lot of times if you were logged in as somebody else and you wanted to record that it was you who made the patch, not the person you were logged in as, you could change that. You click on one of these, you type in the new value. Every time you've changed something, it gets redisplayed sort of behind your back. And so if you click on one of these yes/no things, that means now there needs to be more parameters. They just magically appear. Or if you click on something that means fewer, they magically disappear. It's a very it's a very different from the current model user interface interaction, but a very powerful one. It's much more cumbersome to explain than to learn to do. And so it writes out the file, and now I can load that file into my init file. If you do a show herald command, it lists all the private patches. You can see I already have lots and lots of them. So yes, that was going to be the next thing. So select E. So the demo patch, and this brings up another point. So it records as comments what patches are loaded in the system that you've currently got, so that in case it doesn't work on somebody else's system, they might have a clue to knowing why. But then it has this first form here is the FEP files patched. The files patched in this patch file tells you the source file that the function came out of. So if you made a patch file that was functions from 5 different things, you'd have 5 different files in here. And the note private patch is the comment that I gave for the whole overall patch. And then each patch section has more or less an entire attribute list again. And the reason for that is that the Symbolics list machine allowed multiple Lisp syntaxes to coexist, even ones that used the same package name for different semantics. So the original function, the system was written in Zeta Lisp, and it has a whole bunch of functions that have one semantics, and then Common Lisp came along, the CLTL1 Common Lisp came along, and Symbolics adopted that and made some extensions to that and called it Symbolics Common Lisp. So now there's the exact same functions, but they have different semantics. And there's the exact same user package that inherits from the two of different ones with different semantics. So the package system is fairly elaborate. Then there was CLTL2 and ANSI Common Lisp. Symbolics never was around long enough to actually implement all of ANSI Common Lisp, so it was called Future Common Lisp, the directions that ANSI was going. But they all exist at the same time. There was, for that 386 board, there was a Lisp written by Paul Robertson called Chloe. It also has different syntaxes. You can say, I want to be in a Chloe buffer, and now the code that you compile there will act as if it were running on that 386 machine as well. So it allowed, instead of picking one and restricting you to one, it allowed you to choose any one you want. And because you can make a patch that comes from different files, each patch section has to remember all of that stuff. So you can be putting together one single patch file that has pieces from the user package in 3 different common lisps. I think, what time is it? So I think I've used up all my time. There are plenty more things I can show. Does anybody have a preference? Well, so so what I patched was I actually patched the wrong thing. It copies in when I said add patch, I was in the middle of a function. It just copies that function in the modified buffer. So normally, if I were a developer, I would both save out a new version of the file that I modified so that future releases would get that fix, and I would make a patch. The patch would only include the modifications. If that was an official patch for that system, you just say load patches, and it would get included in everybody at your facility. If it gets released later, it could be released still as a patch. So if you had version number X of a system and it went up to patch 42, and then 6 months later we released the same system, and now we're up to patch 101. If you didn't make a new major version of the system, you would just get the new patches, and then people out at the other sites that got the distributions would get that patch. But most normally, when you distributed something anew, you would build a new version from scratch. So then you'd have version 43 with no patches. But in any case, it would remember which version of the file the code came from. The Lisp machine had version number file system. So every time you wrote a file, the version number incremented. And so the fact that it remembered that I was editing version XYZ of the file is unique globally for the owner of that system. So let me. So one of the things that I wanted to describe before is that when you present something, you don't actually have to have it only be characters. So I can say object circle type string and do graphics with room for graphics draw circle, and if I don't remember exactly what the draw circle arguments are, 40 40 20 filled nil. I've presented the string circle as this graphics thing, and if I say accept a string, notice it's mouse sensitive. If I click on it, I get circle. So you can present anything any way you want, and one of the reasons that dynamic windows was originally thought to be Lisp machine specific is that it, like many other features of the Lisp machine, made use of the hardware when it could. So in the middle of drawing things and creating these presentation objects, there's lots of them created which may not survive the interaction. So when we did that menu at the end of defining the patch, there were lots of little bits and pieces created that when I said end, all went away. But some of them might have had to survive. So those are all created as local variables, but they're the ones that might have to be copied out when you exit the stack frame can be marked with the CUDR codes, and basically the cleanup handler for cleaning up a stack frame knew to find those and copy them into the heap. And this made it fairly efficient to do a lot of things that you would not want to do. Again, this is efficient in the context of 1982 machines when they were slow and there was not much memory, and when you did things that took a lot of memory, you were likely to do paging. These days, who cares? but that's not the only example. For example, when you mark stack frames on the Ivory, those are also marked with CUDR codes, the beginning of a stack frame, so you can quickly scan and find the stack frames. There is a fairly powerful networking facility. So we could talk to different hosts in different ways. Files were objects that were generic, and the syntaxes, you knew from this host that it's let's say a top 20 host. So it had this kind of path name syntax, and this host was an ITS host, and it had this kind of path name syntax. And so you could parse them specifically and put them in a generic format, and then all of the usages, like the editor, would take the generic format and piece together what it needed, and then display them in the path name specific syntax. So even if you had never seen a TOPS 20 path name, as soon as you added that to the system, now ZMAX could use it. And moreover, the file system service could be given by FTP, it could be given by FTS, NFS, it could be given by the list machine file specific file system thing called nfile. And so when you described a host to the namespace system, you said all the possible ones that you could, and you had all the possible ones loaded that you knew how to do, and it figured out what was the best one it could use sort of dynamically. And again, in the early days, this was quite unusual. Read image file. So I'm going to show one more thing, and then I think I'm going to quit. But before I do that, so I mentioned before that we had a C compiler. I'm going to. I had a more elaborate version of this planned, but image file. So I'm going to read this image file. It's a JPEG. Notice when it starts reading, I got the value of this using independent JPEG group star variable, which was nil, and then I set that symbol to T because I wanted to have it use this. I'm going to go to peak, and I'm going to interrupt this process, I hope. With the debugger. So I can debugger any process while it's running. I can interrupt any process while it's running. I can continue, but so I waited too long. So let's do it again. I talk to whoops. Yes. So notice we're in a C frame, and we're seeing C variables, and I can type Control E. Oops. Well, if I had prepared correctly, I could have actually gotten the sources for this are on a list machine file server just in the floor below. But unfortunately, I'm coming in from a subnet that it doesn't know that I'm allowed to use, so I can't. But anyway, it would show me the C in the editor buffer. I could recompile it and continue from it the same way. So I think I'm going to stop there.